Okay, good afternoon, everybody. My name is Rolf Stadler. It's my pleasure and honor to have Henning Schulzwene here for the second time in our Access Distinguished Lecture Series. You probably know Henning as a designer of internet protocols, like a designer, co-designer like SIP or RTP that underlies, internet telephony or internet multimedia applications, but he does a lot of other things as well. And he's going to talk about a different subject today, namely spectrum and spectrum allocation. Let me just, you all already all received a biography of Henning. Let me just mention a couple of things. Henning is first and foremost professor of computer science at Columbia University. He did his PhD at the University of Massachusetts in Amherst. He spent time at Bell Labs. He spent time at GMD Focus in Berlin. I think today it's called Fraunhofer.
Yep.
Then he joined the faculty of Columbia University, has been department chair in computer science. And since 2 or 3 years, he's on leave from Columbia and working at the FTC. He is currently the CTO at the FCC. And I asked him what a CTO actually does, what the role is, and I would like to ask him to comment a little bit during his talk on that. Henning received a lot of awards. He's a very distinguished person in our community. He's an IEEE fellow and has a list of other awards which you can look up on his very long CV. Henning, please.
Thank you. It's really nice to be back in a familiar place, even though it's been a few years. Thank you all for the kind introduction. Let me just maybe say a little bit more, because when you hear these lectures, you probably typically hear distinguished faculty, maybe a researcher from Ericsson or somebody like that who has a more traditional research perspective. While I'm still a faculty at Columbia, my main job right now is as the Chief Technology Officer of the Federal Communication Commission. The Federal Communication Commission, FCC, is, if you turn over any of your electronic devices, even in Europe, you'll see the FCC letters on the back. It is a regulatory entity that does all kinds of things. It regulates traditional communication services like telephone services, and in particular it deals with spectrum management, which I will be talking about today. My role within the Commission is essentially as an advisor on a variety of projects. The Commission, as the name indicates, actually is a commission of 5 commissioners that are appointed by the President of the United States. We have a chairman and 4 other commissioners, and then they have about 1,700 other staff that deal with the day-to-day business of the Commission. So the kind of projects that we're working on that I'm involved with, for example, I worked on the open internet, or as it's often called in Europe, network neutrality order in the FCC. I'm working on video relay service and other relay services for people who are deaf or hard of hearing, sign language type of interpretation. And I'm working on the transition of the existing telephone system to an IP-based system, which is taking place all over the world, including the United States, obviously. And I'm working on a measurement project that I'll very briefly mention somewhere along the way, called Measurement Broadband America, which is a way of estimating performance of consumer broadband, initially in wireline, but now also in the wireless cellular way. We just published an Android app to measure what is your throughput latency in a wireless network, mobile network scenario. And I deal with cybersecurity and any number of other topics. But today I want to focus on probably one of the oldest topics that national regulators in Sweden, in Europe, in the US have had to deal with. Probably the first real need for a coordinated approach, namely how to deal with spectrum. Spectrum is something that we all take for granted, and only once you start looking into that, you'll see that this is actually a very interesting technical, economic, and political policy problem that combines electrical engineering and other pieces to that. So I want to address a few questions today, and I look forward to some questions at the end in that. And this is meant to be kind of a general, I won't go into a great level of detail here. I'm not an RF engineer, so I don't design antennas and things like that. I'm a computer scientist, so I treat it as largely a systems problem, not a radio problem, but hopefully I'll say a few useful things about radios as well. The first question, which is kind of easy to answer initially, but maybe not, is who's actually using Spectrum? Particularly, who's doing kind of computer science, electrical engineering research here? Pretty much everybody, I would imagine. Yep. You probably think of two applications for radio, namely Wi-Fi on your laptop, on your cell phone, and your cellular frequencies, which you generally kind of ignore except when you have to pay for them. And so, but what I'll try to point out that is Spectrum is essentially a history book of telecommunication. It encompasses almost everything which has been invented since the invention of radio still exists in some form or another. And that determines what you can do beyond kind of what we see as a consumer. Can we move to very high frequencies? So everybody knows that spectrum is something that's becoming scarce. You read that in the newspaper, that we need more spectrum because everybody's downloading so many cat videos, and so we all need more spectrum. Where do we find it? So can we move to ever higher frequencies? What's possible, what's not possible? What are some of the trade-offs? Is all spectrum made the same? There are some issues as to why some spectrum is better than others. It used to be that you could basically simply use spectrum which any way you wanted to. You just got it, and then you kept it forever when you had it. And it didn't really matter how efficient you were. That is no longer possible. All the spectrum right now that can be used technically is in use, and so we have to worry much more about efficient usage of that. Kind of like energy efficiency. 20 years ago, come on, you paid for it in some way, but energy efficiency wasn't a big deal. Nowadays, obviously it is for both environmental reasons, and that's less an issue for spectrum, although it is an equivalent of spectral pollution as well, but also simply because you're running out of spectrum that you can just use inefficiently. And we also, a few years ago, thought that we would just simply define radio as just another piece of software in that. That really hasn't happened. I'll briefly talk about why that is. I'll talk about an interesting economics and computer science and electrical engineering problem that's happening in the US right now, but I'll suspect you'll see it in Europe in a few years as well. Namely what's called the TV incentive auction, which is essentially, some of you might have heard of the digital dividend. It's a second version of that, and I'll explain more what that is later. And in general, I'll try to ask lots of questions that hopefully motivate why this is an interesting topic for us as researchers to think about, because it affects what everybody does and can do in that. Let me talk a bit about spectrum licensing in general. And let's take a bit of a kind of bigger picture in that. Why do you do that at all? Why not just simply leave it all to the market, or I might like you to have a Wi-Fi? Generally, as a theoretical level, the reason in economics that people believe you need regulation is generally because you have what's called market failures. A market itself doesn't work well enough in that particular case. So you have private monopolies or competitive market failures. So for example, duopoly, where you have only two competitors. Often, for example, in many places, you only have maybe 2 or 3 mobile services, or one landline companies like you had in most countries, where you had the old PTT provided with phone service and telephone and other data services in that. And you also have social and policy objectives that are not met by the market. For example, for disability access, the market isn't large enough. There aren't enough people with, say, who are deaf or who are blind, so there isn't likely going to be a market for serving those populations. So you typically need to have a government regulatory intervention if you want to serve those. Or the notion of universal access. That's been, if you followed telecommunication policy at all, everywhere we now want broadband to be available to every citizen in a country, in Europe, say. High-speed broadband. How do you make that happen? In many places, broadband, if you deploy fiber, for example, is too expensive. There are just not enough people living there, and it takes so much fiber and digging and trenching to do that, that you wouldn't get that if you just said, well, dear telephone company, just provide service. They would provide services in Stockholm, but they probably wouldn't provide services in very rural areas, simply not cost effective in that. There's law enforcement type of issues that you need to deal with, like safety type things. So one of the things that I won't be talking about, that the reason your cell phone has an FCC or equivalent European sticker on the back is that every cell phone has to be inspected by a laboratory to make sure that you don't care, that it is not a dangerous device. Right? When you think of it, your cell phone is a 2-watt microwave oven in your pocket. Doesn't particularly not confidence-inducing, but it emanates at the same frequency. 2.4 gigahertz is the same frequency that your microwave at home uses, and your microwave at home has 500 or 1,000 watts, so it's a lot more powerful, but your cell phone is a small microwave emitter. And so it needs to be regulated in a way or certified so that it doesn't emit unsafe amounts of radio energy to people. And for other devices, they need to be certified, like by your toaster and your TV. They don't emit radio energy as an intentional emitter. They're unintentional emitters. You don't want them to interfere with other devices, for example. We do consumer education as part of regulators, and there's also economic development. So, for example, scientific research. Let's talk a little bit about radio. So the reason we got spectrum management was the Titanic in the US. So what happened was, among many other things that went wrong when the Titanic sank, was that they couldn't communicate their Mayday, their SOS signal, to other ships in the neighborhood until much too late. The reason was that there was no agreed upon frequency that they would listen to. Not every ship had a radio receiver. This was early on. Radio had really only been invented for 10 years by the time the Titanic sank as a commercial product, if you like. And so immediately afterwards, the Titanic sank in 1912 in the US. The Radio Act of 1912 was the first radio regulation which said basically every radio transmitter has to be licensed. So you have to get a driver's license type thing. You have to register it. And you have to monitor, if you're a ship, you have to monitor one frequency, 500 kilohertz, which is like the medium wave AM, below AM range, for distress signals so that you can help your fellow captains, fellow ships when they're in distress. Then in between 1910 and the mid-1920s, radio for commercial use, for consumer use came into being. So this happened everywhere where you had music and other radio stations that came about. In some countries, most European countries, you had state radio systems, so the state had a radio system. In the US, you had private radio transmitters. And very quickly, people discovered, hey, this is a great way to make money. So you had hundreds and thousands of radio transmitters, and they didn't coordinate, and so there was lots of interference. People would just crank up the power so that they could reach more people, and then would interfere with the same radio frequency a few cities away, and it was a complete chaos on radio waves. So everybody suffered. So in 1927, they said this can't go on. We have to license radio stations as well, and you have to get a license for that, and it's a scarce commodity, frequencies that you could use. This was all, at the time, you could only get medium wave. There was no FM, ultra shortwave radio at all. So you only had maybe 20 or 30 frequencies available to radio stations, so you had to license yourself for that. And so this is when we had the first government entity doing that. And then in 1934, we had the modern, if you want to call it modern, telecommunication law in that. Generally speaking, for radio and TV in the US, it was on a first-come, first-served basis. If you satisfied certain conditions and you paid a fee, you could get a radio station. You just had to locate yourself in frequency and space in places where there wasn't another radio station. But otherwise, there was no particular requirements in that. So we have public radio stations, we have private radio stations as well, just like it now is in most European countries as well. So why do you have licensing at all? I mean, why not just simply rely on a free market type of solution? The biggest problem from a radio perspective is interference protection. So if you had anybody who wanted to put up a radio station, just do that, be it a cellular or a traditional radio type of station that you'd have, then what would happen is you would have so much interference with that nobody could really do a good job transmitting in that. So particularly if you look at the kind of system performance that you get here, you see that in a traditional analog system, performance goes down and down and down as you get less signal strength or more interference. In modern digital systems, they're a bit more robust, but they also essentially, once you exceed their system design limit, they collapse. So basically you get no signal, no picture at all, as opposed to a noisy picture. In the early days, you had no error correction in systems, so it was just raw transmission, and you had no retransmission because it wasn't a packet-based system. So they were very vulnerable to interference, radio interference from other stations. The important part, if you don't have interference protection, it is often very expensive to build a new radio system. A traditional TV or radio station, you have to build a tall tower, you have to buy a studio, you have to set up a radio station itself, so that can cost millions of dollars. And suddenly, once you set that up and you find out that somebody else, maybe your competitor, wants you not to be on the air, they can make life difficult for you. Or they would just be too much, everybody would build radio stations and nobody could transmit, which means nobody would invest money because the risk was too high that would happen. So it's an investment protection and it encourages investment. Think of it as if nobody could buy property for building a house. You always had to be afraid that somebody else was going to put a cottage on your property once you started building houses. And the third reason is that it's a scarce resource, so you want to allocate it to the most efficient and economically beneficial or culturally beneficial use in this. And you want to then also enforce good behavior. Just like you do for homes, for zoning, you tell somebody in that part of town you can only have apartments, the factories have to be in that part of town, and you can only generate so much noise or smoke or whatever in the old days to make it possible for your neighbors to live. In radio, when we think of computer scientists of radio, we generally tend to think of this as, you have a radio wave which has frequencies, and it has exactly like a square type of thing or a rectangle in it. It emits certain frequency and then nothing else. In real life, that doesn't work that way. If you look at, for example, this is a Wi-Fi picture here, you can kind of see it, is you have a main lobe of a transmitter, and then you have side transmitters which are just naturally caused by the system design. So the rules, for example, for radio transmission are such that you are supposed to transmit at full power, and then you have to roll off. You have to protect your neighbors who are in that area, say, already, against your what's called out-of-band emissions, because you just can't physically, impossible, given real filters, you can't have a filter which is just a nice rectangular shape in that. They have a slope in that. So we tend to focus as researchers in networking. If you looked at networking papers, they're probably 99% of all papers probably on two topics. Wireless LANs, 802.11 type things, and maybe 4G mobile broadband. But there are many, many other frequencies and applications which are used. They're just not research topics at the moment. So, for example, you have private fixed networks used by police and firefighters, for example. You have scientific use. So somebody told me a story recently that an inventor of the modern cell phone, Marty Cooper, who had developed the first cell phone at Motorola a few years ago, was getting a prize at a National Academy, and somebody was sitting next to my colleague, radio astronomer, and he said, he was complaining all evening that the invention of a cell phone was the worst thing that ever happened. It was disaster for humanity, because his notion was radio spectrum was for sensing the Big Bang and other faraway ones, and every new radio invention had added noise and made it ever more difficult to hear these really faint signals from billions of years ago that emanated from some long dead star in that. And so this has become a real issue that there's ever smaller slices available for radio astronomy. So for example, in the US, and I don't know how that's in Europe, one TV channel is set aside just for radio astronomy. So there's 6 megahertz of spectrum, which is where there's no TV station, so that the radio telescopes can listen to that. We have medical devices that use radio energy. We have public safety, national security. We have unlicensed devices. We have machine-to-machine communications of all sorts that take place on short range. We have satellites. Well, you probably familiar with direct broadcasting satellites, but there are all kinds of other satellites that are used for more specialty applications. We obviously have broadcasting still, traditional TV and radio broadcasting, and we have critical infrastructure like water systems and power systems, et cetera, that all use that. Transportation, train systems. So for example, right now in the US, they're rolling out a nationwide positive train control system, which makes sure that trains can know where other trains are so they don't run into each other in that. It's a 220 megahertz system at 220 megahertz frequency, not a cellular system, completely separate system that runs in a different spectrum band. So how is spectrum allocated? There are basically 3 ways to do that. The first one is essentially by command and control. An entity, a government entity or some other regulatory entity, just allocates the spectrum in a way that says, this is the best use. We need spectrum for train control, we need spectrum for firefighters, and we just allocate it. It's not sold, it's not anything like that, it's just given to somebody so they can make good use of it. The second one is that you essentially treat it like property. You just treat it like a house, like a piece of land that you sell to somebody, and that has been used now for a commercial cellular type of system. You typically auction it. I'll talk about that a little bit more. And then thirdly is the commons model. So you don't sell it, you let everybody use it. This is the unlicensed model in that. So anybody can use a piece of spectrum for that. By far, the largest amount of spectrum is now used for by property rights, but the traditional model is by command and control allocation. So in the what's called commercial mobile radio service, which is cell service, it's all now done, at least in most countries, done by auctions. In the old days, actually, it was done by what was known as a beauty contest. So you had multiple operators who would come to the regulator and say, I'm going to build this massive, wonderful network. I'm going to offer all these fancy voice services. This was long before data, and it's going to be really cheap to consumers, and I'm going to roll it out in the most remote areas, and hopefully they would be seen as the better one than their competitor in that. That didn't work too well. It was very difficult to determine ahead of time who would really do what they promised to do, and it was really hard to predict what exactly they would do with that. So nowadays, almost all countries auction off spectrum in huge auction, billion-dollar type auction, or billion-euro type auction in that, since the mid-1990s. The first auctions actually were done by the FCC, and it slowly spread. So in the US at least, since the first auction in 1993, $50 billion have been spent by radio-related companies, primarily cellular, on spectrum. So it's a big amount of money. So there are other licensing examples by rule, where you just simply say a certain rule, you have to use certain type of emissions and all of that. And there's first come, first serve as well. To just give you an example, what this looks like is we have federal regulations in the US. This is the rule that's used for the so-called Part 15 operation, which is 802.11. That describes essentially the basic operating principle, namely for unlicenses, you can't generate interference, and if somebody interferes with you, too bad. That's your problem. You can't come running to anybody and complain about it. If you operate a TV station, you can obviously go off and complain. So let's talk about one of the changes which has taken place in the past few years. Namely, we used to have, if there was a new application, you got new spectrum for it. First there was radio, then you got radio spectrum, then TV came along, then specialty medical application. Each one would get their own little piece of the spectrum pie. So this is one example of the spectrum map. This is between 700 megahertz and 2700 megahertz, 2.7 gigahertz. Just as an example, there's obviously stuff much to zero frequencies and there's much higher, but that's the very interesting piece that's used for almost all data pieces. And without going into the details, you can see by just looking at the colors that you have all kinds of different uses. You have some of the colors indicate government use, some indicate private use, some is satellite, some is medicine, some is amateur radio, like the antenna here that's on the building next door. You have TV, you have radio, you have wireless microphones, like the one I'm wearing here, which typically use TV frequencies. All of those are, it's essentially a historical atlas of radio history. Some of it dates back, I said, into the 1920s. Some of it is very recent LTE radio allocation, for example, or radio astronomy or something like that. If you look at the commercial wireless spectrum, again, the US picture, European pictures don't look all that different, just the details differ. It's one of the interesting pieces for historical reasons. Everybody uses the same Wi-Fi frequencies, more or less, at least at 2.4 gigahertz, but everybody for historical reasons uses different frequencies for cellular radio. Some overlap, but some don't, and that's why sometimes when you bring devices, say, to the US from Europe, they may only work for voice, but not for data, and vice versa. So you can see this is all kind of different bands, but interleaved with satellite, GPS is in that spectrum as well, etc. So one of the other things that has happened is that we've had a time-delayed version of mobile access for speed compared to your home residential access. So this is just a timeline roughly as to the speeds that you had for the green one, the landline access like DSL, and fiber to the premises, fiber to the home, and then like 802.11b, G, N, and AC as the most recent one in that. One of the other things that has changed in the last few years is that the old world of spectrum management can no longer work. In the old world, we had mostly, as I said, single-use spectrum. So you get a spectrum and it would be assigned to radar. That's actually a very large amount of spectrum in the 5.8 or 5 gigahertz band is used for radar, like ship radar and military radar and for planes, air traffic control, all of that. Very important stuff, but it's typically one-way non-data transmitter. Land mobile radio, which is what your police officers use, paging, in case you still remember those, but it was single-purpose allocation. You had either government or private use. You didn't mix the two. Either a particular piece of spectrum was used by the military or police, or it was used by private citizens. You never had the same spectrum be used for both. Each band was kind of its own world. It ignored what was happening left and right of it. It just basically treated it as it didn't exist. Usage stayed the same forever. It was radio since the 1920s. You can still, if you took a radio from the 1950s, like a FM radio, like a short radio, it would still work today, just the same as it did when it was bought in 1950s or 60s. Spectral efficiency didn't really matter. As long as you didn't stray outside your spectral band, not a big problem. And if you needed a new application, generally speaking, you went to higher frequencies. This is why we started at very low frequencies for historical reasons and moved to first to from kilohertz to megahertz to gigahertz and higher at some point. Now, all the frequencies, as you could see in the chart, they're all allocated. There is no more open frequency. Somebody is using it. Maybe not intensively, maybe not efficiently, but they're using it. People are using both government and non-government at the same time. You have neighbor issues. So for example, we had a big problem in the US, GPS, that's obviously used worldwide. There was spectrum next door to it, which wasn't assigned to GPS. Somebody wanted to use it. It hadn't really been used all that much, only been used a little bit for satellite. And so they said, hey, the satellite usage isn't really that effective. Let me sell it for telephone, mobile, cellular usage. Suddenly the GPS people said, no, 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 you can't do that, because we assumed that it was really quiet on both sides of our frequency allocation. We have these filters that want to be really soft and gentle, slow, and we pick up a lot of energy next on both sides. It's not our band, but our receivers pick it up. If you put a cellular transmitter in, planes will fall out of the sky, and cars will drive into the river, and all kinds of bad things will happen. You can't do that. We actually had our national parliament, the Congress, have hearings about GPS issues because they were seen as so important, and it was really about interference problem outside neighbor interference problem. We've had this with TV stations and cellular because they're neighbors now, etc. We see change of usage. Satellites might become mobile, for example. Everybody used to talk about maybe we would all have satellite phones. That didn't work out so well. Spectral efficiency is a big issue, and we have kind of run out mostly of higher frequencies to go to. One of the other problems is that the value of bits differs dramatically. Traditionally, we had only voice bits on mobile. Nowadays, obviously, it's mostly data in that. And the cost that we have is now, because wireless is seen as a substitute for landline, we worry about how much does it actually cost to transmit a bit on that. And that actually varies quite dramatically by a factor of several. So this is just as a pointer here. This is where we put up a measurement application recently to find out how fast actually different data sources are. One other point I want to make is we tend to think of wireless as equal to mobile. Often we say mobile phone and cellular phone and all of that is pretty much exchangeable in that. But that's really not helpful as we look at new spectral efficiency issues and as new spectral allocation. Because we really have three broad classes of wireless applications which have very different requirements and issues and very different opportunities in that. And we've often just focused on one of them or treated them all the same. So namely, in the US, we are now starting to replace landline telephone service, classical piece of copper into a telephone line, by wireless services because it's too expensive to maintain the copper loops. And so large telephone companies say, hey, we'll put up a box on your house, and that receives a cellular signal, and it uses your existing in-home telephone, be it business or private, for that. We obviously have nomadic, typically your laptop or your tablet with 802.11, and then we have true mobile applications. But even those differ dramatically, and Gunnar Carlson and I talked about this a little bit earlier today, is that you have very different applications where you have lots of people being together in one place, like a bus or a car, a bus or a train, or you have yourself driving in a car, and hopefully nobody does what this lady does in the picture, namely talk while she's driving, and you have people walking about in an urban area, for example. It matters because the power, the stability, mechanical stability, sort of predictability of your system varies. So for example, if you think of a directional antenna, it's really hard to have a directional antenna when you're walking around. I mean, you're not going to keep pointing to the cell tower precisely in that. Not so hard in a bus. It doesn't typically go straight. Trains even more so. You have handoff frequencies differ, all of that. So increasingly, we will have to treat each one of these cases separately and use the special features of each one of those cases as a way of increasing how efficiently we use the spectrum. One particular concern is that we see increasingly that video content is dominating what we do on mobile devices as well. in the US. I hope it's less in Sweden. People on average watch about 4 hours a day of TV, and it's mostly still old-fashioned TV. It might be over cable, but it is linear type of non-on-demand TV. And indeed, if you look at landline type one, video is at least half the internet is just video content. Now, if we were to all move that to mobile applications, wireless applications, depending on how you look at it, we have an issue. But there's also lots of other type of video applications, distance education, telemedicine, video conferencing, etc. So what happens, for example, if you move all of that to Internet Protocol and mobile one in that? So you would need about 410 gigabytes a month of content. So I don't know, what's your typical cell phone plan these days? 1 gigabyte, 2 gigabytes or so? So we're talking several hundred times of what you're probably using on your cell phone plan today. Let's talk a bit about something that may not have thought about it much. Again, I'm talking mostly about US because it's so much easier for me to get US data, and I just don't know as much about Sweden, but I don't think it differs dramatically, is if you look at the amount of spectrum that different carriers have, we have pretty much 4 big carriers in the US that are nationwide. In that, you see that the amount of spectrum that they have, if you can't read it, is AT&T and Verizon, the 2 largest ones, have about 100 megahertz across the United States, and Sprint, for historical reasons, is not the biggest one, has 170 megahertz. That's for all they use, they have that much TV spectrum. And typically it costs you about, the typical pricing is about $1, roughly order of magnitude, per megahertz per person to buy that type of spectrum. So one thing that we've talked about in the past is software-defined radio. You treat your cell phone as mostly software, and then you could use any frequency anytime. For a variety of reasons, that hasn't worked out. Most cell phones can only now receive 4 bands, like 4 frequency bands, that you have at various slivers. Typically, these slivers are 10 or 20 megahertz at most wide, sometimes in the old days much smaller, because you need different antennas with different wavelengths, smaller wavelengths, meaning higher frequencies, need smaller antennas. You have different filters, which have to be precisely shaped. The A to D converters don't do that wide a frequency. So we haven't really seen a whole lot of software-defined radio, and it's unlikely to see that, which means radio transmitters are still likely going to be pretty much specific to a few bands of frequencies, a handful probably in the next few years, as opposed to be tunable like a shortwave radio where you can tune from 3 megahertz to 100 megahertz type of band in that. That just won't happen, most likely. So one model that we'll see increasingly is that we'll try to see what about higher frequencies. There's plenty of spectrum available at higher frequencies. So the optical spectrum is a few hundred terahertz, so there's lots of room between where we do things now in the gigahertz band and the terahertz band, where you have optical, visible light. And indeed, this is an example of something I measured in Chicago, is even if you compare 2.4 gigahertz to the 5.8 gigahertz Wi-Fi band, the 2.4 is really, really crowded. Lots of transmitters in the same frequency. 5.8, essentially nothing. That was maybe 2 years ago, so it may have changed a little bit in that. Why is that? One of the problems that you have is that the properties of transmission change pretty dramatically between low frequencies and high frequencies. This is why people use FM radio and TV frequencies, which are much lower than typical cell frequencies, because they reach much further. And particularly building materials tend to attenuate higher frequencies, so you can't get inside reception in that. So if you look at, for example, that for cellular, you really have 3 different problems. You have rural problems where you have low density of customers. You need cell tower spacing, which is far, with lots of space between cell towers, because otherwise it gets far too expensive to do that. You want to have miles and miles between cell towers. Urban, you need lots of cell towers because of capacity, so you don't care as much about propagation. But indoors, you again care because you want to reach, you can't put a cell tower in each home. Probably not, you wouldn't appreciate that. And so you need to have radio waves that propagate through walls and windows, for example. So just as one example, people have looked at 28 gigahertz, very much, there's lots of space available there, but it gets reflected because it almost becomes light-like. Windows start to reflect it, and walls attenuate it. And indeed, you have water absorption in some frequencies. So this is for the gigahertz model, gigahertz frequency at the bottom here. You see these blue ones where there are these water molecules in the air intercept radio waves, and so they attenuate the radio propagation. So people are starting to look at higher frequencies, but they're really going to be only for short distances, a few 100 meter, 100 meter, 200 meter type distances. Let me talk a little bit about an interesting thing, auction that's going to be happening in the US, but probably will take place in other countries at some point. The issue that we have in the US that most people don't watch TV using over-the-air broadcasting, antenna on roof type of thing. Only about 10% of the population still watches TV on an antenna. The rest uses either satellite or cable in that. Mostly cable, about 10-15% use satellite. Probably a little different in each European country. But the radio waves in the traditional way aren't really used for that anymore. But people still watch some of it. So one idea was that there is lots of spectrum. So for example, the TV space that's currently allocated in the US is almost 300 megahertz. Remember when I said a few minutes ago that a typical cellular company might only have 100 megahertz available. So 3 times as much is used for TV right now than a single large cell company might have. The total cellular that you have between all companies is about 500 megahertz in the US. It's probably a little more in the US than in Europe at the moment. So what the idea is, in the US, since these are not public stations largely, these are not government-owned stations, but private stations, it would be very difficult to take the spectrum away and says, well, sorry, we like modern cellular stuff better than your old-fashioned TV. We're just going to basically tell you you're out of business. We take a somewhat more subtle approach, namely we simply say, hey, we'll make an auction. If you want to go out of business as a TV station, you can sell your spectrum. We'll have one big auction where everybody comes together and puts their spectrum that they want, and at a price that they want to go out of business or move in with somebody else into some other frequency. And then we'll sell that same spectrum to the cellular companies in that. And we anticipate that will be roughly a $7 billion type auction for that probably sometime next year in this. This is a hugely complicated undertaking because you can't just take a 6 megahertz TV spectrum here or there and just combine them. We have to remove every single TV stations most likely in the US to a different frequency. The US has about 2,000 TV stations all over, large country. And so we have 2,000 TV stations have to all change their radio transmitters. And they don't just have a dial that you can adjust. You have to buy a new transmitter, maybe even a new tower, because the frequency changes in that. So there'll likely then be a set of frequencies in the TV band, how many we don't know, that will remain TV channels, and then there will be a uplink and downlink frequencies for cellular afterwards. I'll just skip that. So one of the other things I'll talk about briefly is spectrum sharing. As I mentioned early on, in the old days, you had a single frequency, single use type of model. Now, so you're kind of a country home where you had lots of space around you and you were the only occupant. Now you have to share, since there simply isn't additional spectrum available. So people have talked about multiple models of sharing. So the commons model, which is the unlicensed model, anybody can use it. There's no special thing going on. But in most cases, you now have existing usages. I mentioned radar, I mentioned radio astronomy, I mentioned other police radio type things. And so you now have overlays and underlays. So an overlay where you're on top of it, so to say, the other frequency, or you're using that below the radio power that the other guy is using in that. And how do you do that? Well, you have models where you allocate as to who is where, so you keep track of the incumbent users who are not going to be very happy if you suddenly interfere with their existing radio usage. The devices can't handle it, and they see no reason why they should suddenly have a competition for that radio band in that. That's where most of the activity is in that. So anybody here working on DSA, dynamic spectrum access? Maybe one or two, yep. So there's a lot of interest. I'm sure you've all written papers on sensing type of things. Nobody so far in the practical world has been using sensing except in 5.8 gigahertz. Actually, that's probably less known, that we've actually been doing dynamic spectrum access for 5 gigahertz with radar. So there are radars in that range, and so they have to be sensed. But what people are talking about is largely database-based approaches. So what you do is you put the incumbent, the existing users into a big database. You draw a circle around them and say, hey, you can have a exclusive use in that area, and outside other people can use it. Say, for example, a TV station. I talk about that particular model in that. But you need to design that in a way that you don't get complaints, or you can't figure out who's interfering with your radar system, for example, in that. These radar systems are usually old and dumb. They have no idea what other emitters there might be. They assumed there was nobody else around. We have at the FCC, we have people who ride around in vans with big antennas on top. They find pirate radios and other interfering transmitters, and they fine you a few $1,000s or more if you are not licensed to transmit on us. But we have to be able to find them. We can't chase after every individual user and home system. So we are now seeing 3 sharing models that are the licensed traditional model. You just rededicate frequencies, like for the TV auction I mentioned. Shared license spectrum, so you have now 2 transmitters, like radio astronomy and cellular in this particular case, and the old license model. So in the shared license model, you have an incumbent user that has priority in the database, and then you have a new user that will actually ask, they find their location, they're mobile in many cases, they determine their location somehow, they send a query to the database and say, anybody using that particular frequency here? And then you might be able to use it, maybe even only temporarily. So in the US, we have started what's called TV white spaces. Anybody know if that's been happening in Sweden yet? So the idea is that in many places, TV channels are available that aren't used for anything. There just aren't enough TV transmitters, particularly in rural areas. So there is now a database out there, several actually. Google runs one of them, Microsoft and a bunch of other people run databases. They're all obviously sharing the same back-end data. That you can ask as a radio transmitter and say, hey, I want to transmit. I want to set up a link between 2 places here. Is this frequency available in this particular region? And can I use it here? And then the database says, yep, you can do that. Or nope, sorry, there's a TV station here, stay away. Or there's a microphone, wireless microphone there. We're also going to be doing the same thing in the 3.5 gigahertz band, so somewhere between the 2 existing wireless bands, where there's also incumbent users, primarily satellite users and radars. So we're going to be ending up with a bunch of bands beyond the ones that we already have today. So when you do wireless research, you really should be looking at more than just the traditional Wi-Fi type bands in that. And also, we are starting to see hybrid components where we have a system where you don't just use traditional Wi-Fi in, say, 5 gigahertz, but Qualcomm, for example, has proposed to use LTE, LTE Advanced, in the unlicensed spectrum. So they would use some channels in the 5 gigahertz band as like a cell tower as a supplemental downlink service to increase your data rate in that. Let me talk before I close on one particular topic that I think will become increasingly important, namely spectral efficiency. It's something that, as a computer scientist, I really never worried much about, but it is, since we now can no longer afford to waste spectrum on people who don't use it terribly efficiently, we have to have some idea as to who uses it how. So the classical model that, if you've taken any radio course at all, is you have a classical model of spectral efficiency based on Shannon. Type of theorem is namely how many bits per second can you stick into 1 hertz of bandwidth. So for example, many systems tend to be that you have for each hertz of bandwidth, you get, say, 1 bit of data rate, bits per second per data rate. So it depends on modulation, your noise, all of these type of things, and there's a limit, again, the Shannon limit, that tells you that. But we also want to have a total spectral efficiency. So for example, some systems need bands, so-called guard bands, which can't be used for anything else. So they're just used to keep 2 different uses separate in that. So that's essentially wasted space that you just have to keep clear to make the system work. Or you have data efficiency. So for example, old digital TV now uses an old version, namely MPEG, MPEG-2 as the data transmitter. We now have MPEG-4, which is roughly twice as efficient, and we might have H.265, which might be another factor of 2 or maybe a little less, be more efficient. So you can use double the amount of data for the same amount of spectrum. In some cases, you can use multicast versus unicast, say for TV distribution. You can use more efficient protocols, or you can use caching and other modes to just not transmit data at all. What we don't have a good understanding for right now is we understand the radio stuff, bits per second per hertz more or less, but we don't understand is the overall system efficiency of that. Let me just look at one particular piece because that illustrates that. It used to be that by the 1G, 2G, 3G, and 4G type of radio, each time the efficiency went up pretty dramatically. You see here the early radio, this is the edge type of early data type of very, very low efficiency in terms of bits per second per hertz, and then LTE, much higher efficiency. So in case you can't read it, it's about 1.4 bits per second per hertz. But as you can see by the shape of the curve, we've pretty much reached the limit of that particular model of increasing efficiency. Some of the other things that we're doing in general to increase increase efficiency is that you will see that increasingly 2G and 3G will be turned off and converted into 4G LTE spectrum. This is a US picture, but increasingly 2G and 3G will just go away, meaning old phones will no longer work. We'll also increasingly add caching to that so that we can have more efficient data transmission in that, so we don't have to retransmit the same information, particularly over backhaul links as well, particularly because caching has gotten much more efficient, for example, compared to spectrum. So in total, what can we do? We can use much more efficient system design. We can use more spectrally efficient transmission mechanisms. Increasingly, we'll also see directional antennas. That's probably the most significant advance that's still available, is instead of transmitting the same information to everybody within, let's say, 120-degree radius of a cell tower, the typical cell site design, you'll now have narrow beacons. Multi-user MIMO, for those of you who are working in that area, is really that model in that, or steerable array antennas, all of that, particularly at higher frequencies, radio frequencies. We'll see that happening. That's probably the single most effective means of increasing spectral efficiency. Again, that's going to be much more interesting for devices that have predictable movement, such as cars and trains and so on, much harder for others. So that was my quick attempt to give you a sense of the vast variety of things that are going on in how to deal with the crisis in spectrum availability and bandwidth. as I hope I could convey, and there's much to be said about all of these, is there is no single solution, but there are lots of interesting, very important technical problems. They don't make any more spectrum. You can't just buy more of it beyond what Mother Nature has provided to us. The physics don't change. They haven't changed in a few million years, since the atmosphere is pretty much what it is today. So we have to deal with what we got. So the idea for spectrum is like for anything else that's scarce. We have to reuse the spectrum. We have to reduce the spectral usage of the same applications, and where we can, we have to recycle the spectrum into new uses as new technologies come along in that. And I think there's lots of interesting problems to be studied, particularly for people who both understand computer science, networking, and who can learn a bit about networking, because those are the problems that are going to be with us for the next decade or more as people want more data, more applications, more cell phones, et cetera. And with that, I'll gladly take questions. Thank you.
Thank you, Henning. Right. Let me ask you, can we take off-site questions, or are we, I'm asking you, can we take off-site questions or no? Okay, okay, very good. Then I open up for questions on the floor. I don't want to run up, so I ask Henning then maybe to repeat the question.
Okay.
Please.
Yep. Yeah. So it's asking about spectrum, if I understood correctly, about particularly for applications that have requirements, say quality of service delay, machine-to-machine type of applications. And how do you provide that in this very limited spectrum you have? Indeed, that's been one of the groups that we have in our Technology Advisory Committee for the Commission is looking exactly at that problem, namely, in the old days, you would have said we allocate one particular range of spectrum. For example, in the US, the electric utilities, electric companies, they want to have a separate spectrum just for controlling smart grid applications. Low latency in some cases, certainly high reliability in almost all of them. And we have said, hey, we show you the map. Where would you like to fit that? Who would you like to kick out of the existing spectrum? So what I'll see increasingly is sharing and allocation that you have, let's say, within LTE quality of service mechanisms, or sharing mechanisms where you have a primary and secondary users. So that, for example, right now is one discussion for vehicular use. So as you know, there's the DSC band for vehicular networks, and now this isn't the 5 gigahertz band. Now this is being discussed as also an extension of the 5 gigahertz unlicensed spectrum. But you don't want to have vehicle collision systems have to wait behind your packet transmitting a video. So there's discussion at the radio level itself. You would have MAC protocols typically that would give inherent priority and thus more predictability to some higher value applications. So you'll increasingly see operating rules which basically say not just here you can use that spectrum and these are the modulation and the emission band you can use, which is what we have traditionally done, is generally we tell people just here's a spectrum, here's kind of how your filter needs to look like, and that's it. You can do pretty much anything else you like. We'll increasingly see kind of MAC level specification where you have to say, hey, if you find another packet transmitted of that kind, you have to wait until they're done. That is probably the only way we can move up, so to say, a little bit the stack beyond just the traditional physical layer, radio layer type of approach. Okay.
More questions?
One more question. Okay.
Actually, I have one, if I may.
Please.
Kind of a fundamental thing. You made the case that we need regulation, really, you know, that is the beginning. And then you showed historically, you know, how spectrum has been allocated and ended up with saying how we can use it more efficiently.
Right.
Let's say, have a clean slate approach. You know?
Mm-hmm.
So we could reallocate everything. So, and we have today's technology and maybe the technology over the next 5 years. You know?
Yep.
How would you go about spectrum allocation?
Yeah, that's a good question. The question that, in some sense, it's, as you hinted at, purely hypothetical because you never get a clean slate.
Yes.
But what you would see is generally is a combination. It depends on what frequency you're looking at. Namely, short-range frequencies, several gigahertz and 2 terahertz, are probably one where a lightly licensed type of mechanism where you don't have an explicit license, but you have implicit coordination rules. So you basically, all you need is a be nice to your neighbor type thing. So you wouldn't really license individual transmitters. You would just simply do what you do for 802.11 is you have certain rules that you can't just blast whenever you like. You have to wait for the others. In that, you have power limits, for example, in that. So a very light type of licensing mechanism in that. But for lower frequencies where you need wide range, the coordination problem becomes inherently more difficult because the number of parties that could potentially emit in that range becomes so large that it's difficult to know who you should coordinate with. You don't know, they're not in the same household, they're not in the same company anymore. And I would imagine it's going to be really very difficult to do that on a kind of pure market mechanism. The problem, and people have, particularly in the academic literature, started a lot about instantaneous auctions, that you would just simply bid for spectrum, not on a multi-year basis, but just for the next 5 minutes. Lots of Infocom papers and similar type of conference papers on that. The practical problem is that because transmitter and tower and antennas are frequency specific, it would be very difficult to plan network investment that way. You wouldn't know how much spectrum you can get. And so how many customers can you serve? How expensive is it going to be to serve those customers? You can't make a business case that way. So I see it as for a longer range mile and above type of, or half a mile and above type of spectrum, very difficult to have a completely automatic, non-licensed type of mechanism evolve, simply because of the investment in billions of dollars, typically, I mean, a major network, probably to build a network in the US-sized country, probably in the order of $30 to $50 billion. It's going to be hard to do that unless you have some predictability over much longer time horizons than the typical implicit auction you would have. The other problem you would have is denial of service attacks and various hoarding type of things that people would speculate in spectrum. That has happened to some extent already. People buy up spectrum. They don't want to use it at all. They just want to hoard it so that other people will find it more useful next year and they'll pay you more than you paid. And so it becomes a money-making thing as opposed to something which is used for actual communication.
Thank you. So if there are no more questions, I would... yes, please. Can you speak up?
Yeah. Yep.
I think you mentioned that the cellular system and cellular bands that we have in the US have historically been quite different. And what are the sort of thoughts and plans we see going forward? And the second part is a lot of the sort of issues that we've seen in compatibility with broadcast systems have been for receivers, for ability of the receivers to discriminate between
Yep. So let me just two very interesting questions. Namely, one interesting question, the last one is how do you deal with receiver issues in general? How do you discriminate that? And the first question, international alignment. So the problem, as you hinted at, is that currently, for historical reasons, countries have very different spectral allocations for particular cellular, which means that mobile devices have to either don't travel internationally well, or they have to have all kinds of bands in there, which makes it more expensive to do that, and you can only do that to a very limited extent. I would imagine that longer term, you'll pretty much, in the band between 600 megahertz and about 3 gigahertz, largely that band will become a data communication band, simply because it's best under current technology useful for wide area networks, kind of cellular national scale networks, and the other uses can probably, in some cases, be accommodated by other existing technologies. So, for example, you could imagine that in the future, wireless microphones like the one I'm wearing would use Bluetooth, as is already happening, and radios for police and fire, they would use LTE, as is starting to happen. And so you don't need that many really dedicated non-communication application in that. A little bit of radar will remain. So my hope is that longer term we'll get alignment happening at least over large fractions of that band. So certain pieces might be carved out that you can't use. The second piece you mentioned is a very interesting discussion, namely the neighboring issue. In the old days, pretty much people only worried about out-of-band emissions. So you had to be a nice sender, but they didn't really care what receiver you were. There's no rules on how good your receiver needs to be, and I mentioned the GPS example. Recently, we've been exploring, a number of people in my group have been exploring, are there ways to essentially what's called a harm threshold. So essentially, when you license a spectrum, you're told, we don't know who your neighbors are going to be. They might change possibly. I mean, instead, there might not be a satellite there, there might now be a cell tower there, but unless the interference goes above a level that we describe, you can't come to us and complain about your new neighbors. So this is essentially give you predictability. You better design your receiver well enough that it suppresses or can deal with those type of neighbor interference or even leakage into your band without you then saying, no, your neighbor can't move in here, as has happened, as I said, for GPS in particular and other uses as well. So this is a harm threshold model where you essentially specify not the receiver performance, that has been discussed as well, but is very controversial, but basically is a don't complain model in that, and you better deal with it, and you can deal with it either by accepting lower performance, if maybe in some cases that's the best way to deal with it, or by building better receivers so that your receiver can discriminate the signal by error compensation or filtering or other mechanisms, signal processing mechanisms, interference cancellation, et cetera, can deal with those interfering transmitters. So that's a very hot research area right now as to how do we specify that in a way that ensures predictability, because the problem we have in the radio realm is that systems stay around for decades. They almost never go away, cellular radio being somewhat of an exception, but even there, usually they last for 10, 15, 20 years, and so you have to build systems that are have long-term designs.